When we picture a star dying, we usually think of it getting old, kind of running out of gas. But that's not really what's happening. We need to completely reframe how we think about this. This isn't a story about age. It's a story about physics being pushed to its absolute, unbreakable limits. Because that's the real question, isn't it? Every single star, our sun included, is this gigantic ball of matter that's constantly trying to collapse under its own incredible gravity. So what's holding it up? And more importantly, what happens when that support system just fails?
All right, so let's start with the basics. It all boils down to this incredible cosmic tug of war. On one side, you've got the relentless, crushing inward pull of gravity, and on the other, you've got some kind of outward pressure pushing back. For a star to even exist, these two forces have to be in this perfect, delicate dance. And this is the part that's so crucial to get. A star doesn't collapse because it gets old. It collapses when it smacks up against a fundamental physical limit, a point where the laws of nature themselves say, nope, that's it, you can't go any further. This is a story about mass, density, and some really weird physics. Okay, so let's look at the first line of defense, the one we're all familiar with, nuclear fusion. Deep in the core of a star, all that fusion creates immense heat and pressure that pushes outwards. That thermal pressure is what's holding up our sun right now. But it has one fatal flaw. It needs fuel. For the really big stars, this whole process is like climbing a ladder. The star fuses hydrogen into helium, then helium into carbon, and just keeps forging heavier and heavier elements in its core. Every step up that ladder releases energy, which keeps gravity at bay. But this ladder doesn't go on forever. It has a final rung, and that rung is iron.
And this is where everything goes wrong. Fusing iron doesn't release energy. It actually consumes it. It's the ultimate cosmic ash. So when a massive star's core turns to iron, the fusion engine just shuts down. Instantly, the outward pressure is gone. And just like that, gravity wins the first round. The core starts to collapse. But just when you think it's all over, just as the star seems totally doomed, a new, much weirder force slams on the brakes. The collapse is stopped by a shield that isn't born from heat, but from the bizarre, frankly strange rules of quantum mechanics.
It's called Electron Degeneracy pressure. And you can think of it like this. The universe has a fundamental rule that says you can't shove two electrons into the same tiny box with the exact same properties. So as the core gets crushed, the electrons are forced to push back, creating this incredibly powerful, rigid pressure that has absolutely nothing to do with temperature. This is what supports a white dwarf star.
And this shows you the huge difference. Thermal pressure from fusion, it's dynamic, it's hot, but it needs a constant supply of fuel. Degeneracy pressure, on the other hand, is a cold, mechanical force. It only cares about density. It's a way, way sturdier line of defense, but it's not infinite. It has a hard limit, a non-negotiable number, 1.44 times the mass of our sun. This is the Chandrasekhar limit. And it's one of the most important numbers in all of astrophysics. It is the absolute maximum mass that electron degeneracy pressure can possibly support, period. So, what happens if you push past it? Well, the electrons get squeezed so tight, they're forced to move near the speed of light, the ultimate cosmic speed limit. And at that point, Einstein's special relativity completely changes the game. The pressure just can't keep up with gravity anymore. The quantum shield doesn't just bend, it shatters, and the collapse resumes, this time with catastrophic violence. As that core implodes, electrons and protons are literally crushed together, forming a solid ball of pure neutrons. A neutron star is born. And this creates a new, even stronger quantum shield. But now we enter the realm of general relativity, where gravity itself starts to cheat. So this new shield, neutron degeneracy pressure, works on the same quantum principle as before, just with neutrons, and it's insanely powerful. But at these densities, something truly profound and, frankly, terrifying happens. Okay, you gotta stick with me here, because this is where Einstein's general relativity just flips the whole script. See, we think of gravity as coming from mass, from density, but Einstein showed us that immense pressure also creates gravity. And in a neutron star, the pressure is so astronomical that it starts generating its own significant gravitational field. So just think about what that means for a second. The very pressure that is holding the star up
is now adding to the gravitational force that's trying to crush it. The star's own defense mechanism is actively helping its enemy. It's a total relativistic betrayal.
And this leads us to yet another unbreakable limit. It's called the Tolman-Oppenheimer-Volkoff limit, or the TOV limit. Now, we don't know the exact number. It's somewhere between 2 and 3 times the mass of the sun, but we know it's there. And if a neutron star goes over it, this feedback loop becomes unstoppable. More pressure creates more gravity, which creates more pressure, and nothing can stop the collapse into a black hole.
So, is that it? Is a black hole the only final option? Well, physicists have definitely wondered if there are other, even more exotic states of matter out there that could provide one last desperate line of defense beyond even a neutron star. And we are talking about some truly wild stuff here. Things like quark stars, where neutrons themselves dissolve into a soup of their fundamental parts. Or maybe boson stars, held up by a totally different kind of quantum pressure. Some theories even play with ideas like negative vacuum energy. But here's that recurring theme, right? The central lesson of this whole cosmic journey. It seems that every single one of these theoretical support systems, no matter how exotic or powerful, also has a maximum mass, a fundamental, unbreakable limit. There appears to be no such thing as an infinitely strong pressure. And that brings us to the ultimate conclusion of this whole story. After watching every single line of defense fail, one after the other, we can finally understand the true nature of gravity's final victory. What we've seen is this incredible cascade of failure. A star's thermal pressure fails when it runs out of fuel. A white dwarf's quantum shield fails at the 1.44 solar mass Chandrasekhar limit. A neutron star's shield fails at the TOV limit, betrayed by its own pressure. Each step just leads to a denser object with an even higher, but still finite, breaking point. And this is the single most important takeaway. Gravity doesn't have to do anything special to win. It doesn't need to get stronger or power up. It just is. It wins because every other force in the universe, thermal, quantum, nuclear, you name it, they all have a breaking point. It is the universe's most patient and persistent force. It just waits. It waits for fuel to run out. It waits for quantum shields to be overwhelmed. It waits for the laws of relativity to turn defense into offense. Gravity simply waits for everything else to hit its limit. Which leaves us with one final, pretty profound question. If every known and even every hypothetical form of matter has a fundamental limit beyond which it cannot support itself, then what does that imply about the ultimate fate of all matter in the entire universe? Given enough time and enough density, what is the final state of everything?